This video will focus on the architecture of automated resilience, specifically stress testing production microservices at a massive scale. Distributed systems, unlike monoliths, are fragile. A minor transient network timeout or database lock can propagate through dependency chains, causing complete platform outages. Infrastructure chaos is no longer sufficient for resilience testing. Modern testing needs application-level faults, specific framework exceptions, and targets internal error handling logic, moving towards state and data consistency validation and automated traffic replay. Introducing CAST, an end-to-end resilience testing solution for production. It offers high fidelity by replaying production traffic against application-level faults, high scalability by pruning test spaces, and high automation by orchestrating a fail-fast execution lifecycle. A major hurdle in traffic replay is state dependency. Production traffic is time-sensitive and stateful. Blindly replaying recorded requests can fail due to issues like expired tokens or timestamps. CAST uses dynamic variable identification via two-stage heuristics. This payload-centric approach treats services as black boxes, achieving a 98.3% replay success rate without needing source code access. The combinatorial explosion of the test space is a challenge. 6 hours of production traffic yield millions of traces. Exhaustive testing against every potential fault injection point is mathematically infeasible. CAST employs a complexity-driven strategy for trace selection. It aggregates redundant user interactions and targets intricate, failure-prone execution paths, creating a concentrated test suite. Fault injection targets are defined by a strict component, framework, method tuple. This allows for fine-grained, application-level fault coverage, differentiating between functionally identical operations implemented with different frameworks. Target pruning eliminates intratrace redundancy. When a trace has multiple invocations of the same endpoint, the fault is injected only at the final invocation. This rigorously tests the system's ability to roll back a fully staged transaction. Pruning also uses data flow dependency analysis. By prioritizing upstream producers and asynchronous secondary writes, CAST targets critical, silent failures, bypassing isolated downstream tests. The fail-fast execution model is critical. CAST batches fault tests into a single run. If any test fails, the system immediately halts and initiates a hard restart to prevent state contamination. Resilience is defined by phase-based performance criteria: startup, fault injection, and recovery. The oracle verifies expected failure during injection, and critically, a return to a healthy operational threshold upon fault clearance. Naive testing can fall for the illusion of the API boundary, where an HTTP 200OK masks hidden subsystem failures. CAST places granular assertion points at internal dependencies, bypassing this illusion. CAST solves the tension between coverage and cost. By combining complexity-based trace selection with a history-aware pipeline, the system learns weak points over time, achieving cumulative coverage without exhaustive daily computing costs. CAST successfully automated the discovery of critical flaws in high-volume, multi-team environments at Huawei Cloud. Over 8 months, it discovered 137 potential vulnerabilities across 4 large-scale applications. The graph shows the coverage versus cost inflection point. In controlled benchmark testing, CAST achieved a 90% detection coverage. The pruning heuristic works, showing that testing the top 100 most complex interfaces captures the vast majority of vulnerabilities. Cumulative coverage outpaces perfect prioritization. A history-aware execution framework accumulates coverage over time, offering a more robust path to reliability than rare, massive testing events. Engineering trade-offs are inevitable. CAST intentionally trades absolute precision, often seen in theoretical perfection, for operational feasibility and scale. A deployed system that finds 80% of bugs is more valuable than a perfect system stuck in a lab. CAST enables proactive discovery over reactive firefighting. Resilience must be continuously verified, and CAST provides the blueprint for transforming unpredictable failures into automated, manageable data.